Hi everyone, today I will present you my research about the muon bundles on the ongoing effort of the IceCube detector to study the extremely high energy neutrinos. So this presentation contains 4 parts. The first one is a brief introduction about the neutrino astronomy, and the second one is a brief description about the extremely high energy neutrino detection and main background. And the last 2 are a short presentation of my first results. Start with what is an extremely high energy neutrino. It's just a neutrino with an energy above 10 PeV. It can be astrophysical if it is produced directly in point-like source, like active galactic nuclei or GRBs, or cosmogenic if it's produced during the interaction between the ultra-high energy cosmic rays and the cosmic microwave background or the extragalactic background light. So that allows us to study different things. So for example, the astrophysical sources, the production mechanism, the acceleration process, or to trace the origin of the ultra-high energy cosmic rays, their composition, spectrum, and source distribution. And study extremely high energy particle allow us to constrain some astrophysical model and test some fundamental physics at energies not accessible at Earth. So brief and quick description of the IceCube detector, of course. So it's a neutrino detector, which is designed to detect the trunk of light produced by secondary particle, produced during the interaction between a neutrino and a nice nuclei. So the main target of this detector are the neutrino from the northern sky, using the Earth as a shield against the atmospheric background. And it is optimized to detect neutrinos with an energy between 100 GeV and 1 PeV, and it can go down to 10 GeV using its central and denser part, deep core. It's also possible to probe higher energies between 1 PeV and 1 eV, even if the detected events are really rare. And my study is to focus on the southern sky and in this energy range, of course. You can find 2 different types of events in IceCube. The first one is a muon track produced by a muon, of course, and which will produce a long extension inside the detectors. And the second one is a cascade event, which is just a spherical distribution of the light inside the detectors. And there's 2 beautiful movies. You can see the propagation of the photons inside the Antarctic ice. So a short state of art of the extremely high energy neutrino detection for the moment. So with IceCube, we observe a drop in the astrophysical flux in the PV regions. We have only a few detected events in this energy range and no event beyond 10 PV. And we have this beautiful outlier, which comes from Chemtrinet, that just detect a muon with an energy of 120 PeV produced by a neutrino with an expected energy around 220 PeV, which is just huge. So it's not an easy way to study and to detect the extremely high energy neutrino because, as you know, the interaction cross-section of a neutrino increases with its energy. So the Earth becomes opaque to neutrino, and we have to focus on southern, so downgoing, and close to the horizontal event. And the Earth is no longer a shield against the atmospheric background, which becomes omnipresent, as you can see in this plot. And the goal of my research is to make a distinction between the main atmospheric background in this energy range and the signal induced by an extremely high energy neutrino, a muonic extremely high energy neutrino. And the main background is the muon bundles, which is just a group of muons which is produced inside an atmospheric air shower, and that will reach the detector depth and let inside the detector a signal which is really close to the one of an extremely high energy neutrino. And I want to study this muon bundle to find some characteristic that will allow us to train a machine learning model to make an even classification between the background and the extremely high energy neutrino. So for the moment, I'm working on simulation but I will apply it on true data in a second time. So let's start with my results. But I need to introduce you the concept of multiplicity, which is just the number of muons that compose our bundle. And the first characteristic that I want to present you is the lateral extension. So if you look at a muon bundle, you can see it has a spread inside a cylindrical volume. And the lateral extension is just the radius of the circular front, circular front space of this cylinder. So how to get this radius? We just compute the center of gravity of the light distribution inside the detectors. We project the total charge collected by each dome in the plane, which is perpendicular to the track and that contains the center of gravity. And we just draw a circle that contains 95% of the light distribution. That we get this plot, and you can see here for a small radius, so lateral extension, that it's sensitive to the multiplicity of the bundle. So the blue line is just a single atmospheric muon, and all the other lines are bundles with more and more muons. The next characteristics is the stochastic losses. So when a particle passes through the detector, it will lose its energy, but non-uniformly. You will see some sudden energy deposition due to Bremsstrahlung or pair production. And we can characterize the stochastic losses of a track using a parameter named the smoothness. And we get this plot where you can see here is the yellow line, the multiplicity 1, which is really more stochastic than, for example, the red line, which are muon bundles with more than 100 muons. The last characteristics is the residual time, which is just the difference between the true arrival time of a muon at an optical module and an expected one without any scattering during its travel. And you see a really big difference in this graph where you will never have any negative residual time for a single track. And you can have, due to the geometry of the bundle, some negative residual time for the bundles. The last thing that I want to present you is a new event reconstruction to reconstruct, so of course, events which are produced by muon bundles. So when we are reconstructing some event, we are using this Cherenkov cone that you all well know. But the idea is to use a truncated Cherenkov cone to simulate this circular front face of the bundle. So if the dome is inside the cylinder, we will use a plane wave Cherenkov emission. And if the dome is outside of the cylinder, we will use just the usual Cherenkov cone emission. But it's a model which is right now building by Catherine Rowling. So the first result that we get is this plot, where you can see two different reconstruction methods, both of them using the Devil's Tower geometry, and compared with the true radius of the bundle. You can see that it's not really accurate for the moment, but we are working on this. That brings us to the conclusion. So I present you different characteristics and a new event reconstruction method, which seems sensitive to the multiplicity of the muons. And the next step is to use it as a feature to train a machine learning model, which will probably be a graph neural net to improve our event classification. So thank you for your attention.
Thank you, Thomas. Are there any questions?
Which are typical real multiplicities that you get?
Okay, that depends a lot of the energy that you are probing, but oh, sorry, fine. So that depends really of the energy, but the main part is between 10 and 100 muons inside your bundle.
Where? Oh, sorry.
Yeah, thanks for the nice talk. Maybe it's super obvious to everyone else, but why is it called Devil's Tower?
Okay. It's because there is a mountain in the US named the Devil's Tower who has this characteristic shape of just poop, and it's truncated.
Thank you.